In this episode, we move from privacy concepts that sound sensible in conversation to the practical skill that makes those concepts enforceable in real systems, accurately modeling how data travels from where it first appears to where it ultimately lands. Beginners often picture data as sitting in one database, but modern products behave more like networks of services that copy, transform, forward, and store information in many places at once. When you can model a data flow accurately, you can answer questions that matter, like what is collected, why it is collected, who receives it, how long it persists, and what happens when a user wants access or deletion. When you cannot model the flow, the organization relies on assumptions, and assumptions are where overcollection and surprise usually hide. Source-to-sink thinking forces you to follow the data all the way through, including the parts that are easy to forget, like logs, analytics, backups, support tools, and vendor platforms. The goal here is to learn how to build a reliable, decision-ready view of data movement without getting lost in implementation details or drawing fancy diagrams you cannot maintain. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A good data flow model starts with language discipline, because the words you use determine whether your model describes reality or merely describes what you hope is happening. A source is not only a form field on a website. It can also be a device sensor, a browser header, a cookie, an advertising identifier, a location signal, a server-side event, or a support conversation. A sink is not only the main database. It can be a data warehouse, an analytics platform, a logging system, an error reporting tool, a backup archive, a message queue, or a vendor system receiving a copy. Between source and sink, data is transformed, enriched, joined, filtered, and sometimes duplicated, and those transformations often create the privacy story. Beginners commonly say we collect email and forget that email might appear in multiple forms, like plain text in one system, hashed in another, and embedded in tickets or logs elsewhere. Accurate modeling demands that you define what the data element is, what it represents, and how it changes, because the privacy impact depends on the real content, not on the label. When teams share a precise vocabulary, modeling becomes collaborative instead of argumentative. Once terms are clear, you can begin by choosing a single purpose and a single user journey as the anchor for the model, because modeling everything at once produces a fog instead of clarity. For example, you might anchor on account creation, checkout, password reset, or location-based recommendations, and then build outward until you reach every sink that receives data from that journey. This focus matters because the biggest modeling errors come from skipping steps, and people skip steps when scope is vague and the flow feels endless. A beginner-friendly approach is to narrate the journey as a sequence of moments where data is generated, such as when the user types something, when the device reports something, when the server records something, and when the system shares something. At each moment, you ask what data exists now that did not exist before, and what system can see it. Modeling this way keeps you grounded in reality, because it ties the flow to a feature and a purpose. It also helps you detect unnecessary collection, because when you cannot explain why a data element appears at a particular moment, that is often a sign it is not truly needed. The moment you identify a source, you need to capture the context that makes the source meaningful, because data rarely arrives alone. A user typing an address in checkout is not just an address. It is also tied to time, device, account state, and potentially marketing context like campaign tags. A sensor reading is not just a signal. It is tied to location, frequency, and who might be affected, including bystanders. A server event is not just a record. It often includes identifiers, timestamps, and payload fields that can unintentionally carry sensitive content. Beginners sometimes model only the obvious fields and miss the metadata, yet metadata is often what enables tracking and inference. For accurate modeling, you treat context as part of the data because it changes identifiability and sensitivity. You also ask whether the source is active or passive, meaning whether the user intentionally provides the data or whether it is collected in the background, because passive sources tend to carry higher surprise risk. If you capture context early, later decisions about minimization, transparency, and retention become much easier because you are not discovering hidden data types after the system is already built. A common mistake in data flow modeling is stopping at the first server that receives the data, as if the first storage point is the end of the story. In reality, systems are designed to move data, not to hold it in one place, and the privacy risk often grows as data spreads. A web request might be processed by an application server, forwarded to a payment processor, logged by an observability tool, copied into an analytics event stream, and stored in a warehouse for reporting. The user never sees these steps, but they determine who has access and how long the data persists. Accurate source-to-sink modeling therefore treats the first collection point as the beginning of the map, not the destination. You ask, for every system that receives data, whether it forwards the data elsewhere, whether it enriches the data with additional fields, and whether it stores a copy. Beginners often assume internal systems are the only recipients, but integrations can create silent side routes to third parties, especially through embedded libraries and default logging. A complete model reaches the sinks that matter, including downstream stores that were not part of the original feature team's plan. Transformations deserve special attention because they can change the privacy nature of data even when the underlying values look similar. When a system hashes an email, people sometimes treat the result as anonymous, yet a stable hash can still function as a persistent identifier that supports linking across datasets. When a system generates a risk score, it creates a derived attribute that can affect a person's treatment, even if the raw inputs were ordinary. When a system aggregates events, it may reduce identifiability, but only if aggregation is done at a level that prevents singling out individuals or small groups. Beginners sometimes treat transformation as a privacy win by default, but transformation can also increase risk by enabling inference or by creating new data categories that did not exist before. Modeling transformations means recording what the system does, why it does it, and what the output enables in terms of linking and decision-making. It also means capturing whether raw inputs are retained after transformation, because retaining both raw and derived data often increases exposure without adding real value. When transformation logic is modeled clearly, teams can choose safer designs, like using short-lived tokens instead of stable identifiers or limiting the retention of raw data once derived metrics are produced. Data flow modeling must also include identity and linkage decisions explicitly, because identity is the thread that turns scattered events into a story about a person. A system might use an account ID, a device identifier, a cookie, a phone number, or a combination, and each choice affects how easily behavior can be linked across contexts and time. Beginners sometimes assume identity is binary, like either we know who someone is or we do not, but modern systems often operate in a gray zone where linkability exists even without a name. For example, an anonymous browsing session can become linked to a person when they log in later, and the earlier events can suddenly become personal data in retrospect. Accurate modeling captures when and how linking occurs, such as when a session ID is associated with an account, when a device is added to a profile, or when data is joined in a warehouse. This matters for transparency because users may not realize that behavior they thought was anonymous becomes tied to them later. It matters for minimization because stable identifiers increase surveillance capacity. It matters for security because identifiers are often the keys that make datasets valuable to attackers. If you model identity linkage honestly, you can place boundaries where they belong. One of the most frequently missed sinks in beginner models is logging, because logs are seen as technical leftovers rather than as real data stores. In practice, logs can contain identifiers, full request payloads, error messages, and sometimes user-generated content, especially when debugging is enabled or when errors cause full context capture. Logs are also often retained longer than application data because retention defaults are set for operational convenience and then forgotten. Accurate modeling treats logs as first-class sinks, documenting what is logged, where logs are stored, who can access them, and how long they persist. It also captures whether logs are forwarded to vendors, because observability platforms often ingest logs into external systems. Beginners sometimes assume logs are safe because they are internal, Yet internal access can still be broad, and exporting logs for troubleshooting is common. Modeling logs helps you spot where privacy promises can be accidentally undermined, such as storing sensitive fields in error traces or capturing full URLs with sensitive parameters. When logs are included, you can design controls like field redaction, structured logging that avoids sensitive payloads, and retention limits that match the true need. Another easy-to-miss sync is analytics and event tracking, especially in-app tracking that uses embedded components that generate their own data flows. An event might start as a simple signal like button clicked, but it can carry a payload that includes user IDs, device details, page context, and product information that becomes sensitive in certain contexts. Analytics data often flows to multiple destinations, such as a vendor dashboard, a data warehouse, and a marketing attribution system, each with its own retention and access patterns. Accurate modeling captures not only that analytics exists, but which events are sent, what fields they contain, and where the events go. It also captures whether events are filtered based on user choices, because a privacy setting that does not change event routing is a broken control. Beginners sometimes treat analytics as harmless because it is for measurement, but measurement data can be used for profiling when identifiers are stable and retention is long. Modeling these flows helps teams reduce unnecessary fields, shorten retention, and restrict sharing with third parties. It also supports transparency, because you can explain tracking behavior honestly only when you know what is actually happening. Vendor and service provider flows must be modeled from source to sink as well, because data rarely stops at the first external recipient. A support platform might store ticket content, attachments, and account identifiers, then replicate those into analytics and reporting systems. A payment processor might receive billing details, then store records for compliance, then share data with fraud systems under its own policies. A cloud provider might host storage, while subcontractors handle monitoring, backups, or customer support, creating additional sinks you must account for. Accurate modeling records what data is sent to each provider, what purpose the provider serves, what restrictions apply, and what downstream subprocessors exist. Beginners sometimes assume the contract solves the risk, but modeling is still required because the practical question is where data sits and how long it remains. Modeling vendors also helps with incident response, because if an incident occurs, you need to know which systems hold the data and who to contact. It helps with deletion, because user data in vendor systems often require separate workflows. When vendor flows are modeled, you can set measurable controls and verify that data sharing is minimized and governed. Retention and deletion should be represented in the model as properties of each sink, not as a single global policy statement. Two systems can receive the same data and treat it very differently, with one enforcing a short retention period and the other retaining indefinitely by default. A robust model, therefore, includes how long each sink retains the data, whether retention is configurable, and how deletion is implemented. Beginners often assume that deleting a user in the main application deletes everything, but deletion is usually a distributed process that must reach warehouses, logs, backups, support tools, and vendors. Modeling the lifecycle also includes derived data, because a system may delete the raw record but keep a derived profile or score, which can still affect the user. It also includes backups, because backups can preserve snapshots that are hard to delete quickly, and this reality must be reflected in expectations and commitments. Accurate modeling supports realistic promises because you can explain what is deleted, what is retained for legitimate reasons, and how long that retention lasts. When life cycle is part of the map, privacy becomes manageable because teams can see where controls must be built. Modeling data flows accurately also matters for rights and user requests, because rights become operational only when the organization can find and act on data across the full set of sinks. If a user asks for access, the organization needs to know which systems hold their data and how to retrieve it reliably, including where identifiers differ across systems. If a user asks for deletion, the organization needs to know which sinks can delete, which sinks can only restrict access, and which sinks retain data for defined reasons. Beginners sometimes think rights requests are handled by a customer support script, but the real work is data discovery and coordinated action across systems. A good model captures how identity is represented in each sink, such as account IDs, email hashes, or device identifiers, because mismatched identifiers are a common cause of incomplete responses. It also captures dependencies, such as whether a vendor must be contacted or whether an internal pipeline must run to propagate deletion. When you can point to a clear source-to-sink model, rights handling becomes less error-prone and more consistent, which improves trust and reduces legal risk. Modeling turns rights from an abstract promise into an executable process. Accuracy requires continuous maintenance, because data flows are not static, and the most dangerous models are the ones that are treated as permanent truth while the system evolves underneath them. New features introduce new sources, new events, and new vendors, and even small changes like adding a debug field can create new sinks in logs and analytics. A robust approach treats the data flow model as a living artifact tied to change management, so certain changes automatically trigger updates to the model. Beginners sometimes think that maintaining a model is busy work, but without maintenance, teams make decisions based on outdated assumptions, which is a recipe for surprise and drift. Maintenance does not have to mean rewriting everything. It can mean updating the parts affected by a change and verifying that those updates reflect reality. Verification matters because people can describe a flow incorrectly, especially when relying on memory rather than on observed behavior. When models are kept current and verified, they become a shared reference that reduces confusion across teams. This shared reference makes privacy work faster because teams spend less time arguing about what the system does and more time deciding what it should do. An accurate source-to-sink model is also one of the best tools for spotting privacy risks early because it reveals patterns that are hard to see when you look at systems one at a time. For example, you might notice that the same identifier is being sent to many third parties, increasing linkability, or that the same sensitive field appears in multiple logs, increasing exposure. You might notice that retention is inconsistent, with one system deleting quickly while another keeps data indefinitely, undermining your commitments. You might notice that a user setting affects what is displayed but not what is transmitted, meaning the control is more cosmetic than real. Beginners often try to assess risk by reading policies or listening to descriptions, but models reveal risk structurally by showing where data goes and what it touches. This structural view supports better design, like reducing the number of sinks, narrowing what fields are shared, and ensuring that choice and deletion propagate consistently. It also supports better communication because you can describe data practices with confidence when you have traced the flow. When models guide decisions, privacy becomes a property you can design and verify, not merely a principle you can recite. Modeling data flows accurately from source to sink is the practical craft that turns privacy from an idea into a system you can manage, improve, and defend. You begin by using precise language so sources, sinks, and transformations are described honestly, and you anchor modeling to real user journeys so scope stays meaningful. You capture context and metadata because they shape identifiability, and you refuse to stop at the first storage point because modern systems spread data across many recipients. You document transformations, linkage, logs, analytics, and vendor flows because those are where hidden exposure often accumulates. You treat retention and deletion as properties of each sink, which makes lifecycle commitments realistic and enforceable. You connect the model to rights handling so access and deletion requests become operational rather than aspirational. You keep the model current through change management and verify it against real behavior so it stays trustworthy. When you do all of this, your organization can make better choices about minimization, sharing, and control because it finally knows, in detail, what it is doing with people's data. That is what source-to-sink modeling delivers: clarity that drives safer design, stronger operations, and more trustworthy products.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.